Today's lesson on gases and temperature change is using the audio system by FrontRow technology. So sound that you're hearing in this video is courtesy of FrontRow. So the temperature of a substance is defined as the measure of the average kinetic energy of the molecules in that substance. So temperature and volume. We looked last class at Boyle's law, and Boyle's law dealt with pressure and volume. So today we're going to be looking at how volume and temperature pretty much relates to one another, and primarily by the studies of Charles, French scientist who investigated the expansion rate of nitrogen, oxygen, hydrogen, carbon dioxide in balloons. He found that these gases all expanded by the same ratio. So for each degree Celsius increase in the temperature, all of these gases would expand by a certain fraction. So he saw a correlation between volume and temperature. For each degree Celsius decrease in the temperature, their volume would decrease by the same fraction. So he noticed that there was an increase, if temperature increased, there was a decrease if there was a temperature decrease. Okay, so they know that there was a direct correlation between temperature and volume. So Kelvin scale and absolute zero. So we're going to be looking at a new temperature scale. We've been using degrees Celsius, and we're actually going to use a different set of measurements. But now what we're going to look at now with what Charles has studied is the following. Okay? He labeled on this axis temperature and volume, and what he noticed was as the temperature increased, so did the volume. Okay? What he also noticed was pretty much as the temperature decreased, it was also. So eventually he realized there was a point in which technically molecules would cease to move. Okay? So this was where he labeled at minus 273 degrees Celsius. And we're going to see now a new scale for measurement. Notice how the temperature scale, right, at zero is not the lowest, right? And usually when we're graphing, we always start at the axes at zero, right? But temperature can go into the negatives. In 1848, Lord Kelvin, Scottish scientist, realized that at minus 273 degrees Celsius, molecular motion would cease. It would stop. Okay, that's more of on a hypothetical. Okay. At this temperature, kinetic energy would be technically considered at zero. Okay. So what we used now was a new temperature scale. We weren't going to use the degrees Celsius. We were actually going to use something called a Kelvin scale. So the volume of a gas would hypothetically also be zero, which means if you had a gas and it all of a sudden the motion ceased to exist, then all of a sudden then technically we wouldn't have any molecules really left, right? The volume would be zero, right? So if we go back to this scale here, right, the volume is decreasing as temperature is getting colder and colder. But now look at this. Imagine the possibility of this. How do you go from a somewhat of a volume of a gas to a volume of zero, to having literally nothing? Right? That's why it's considered a hypothetical. Okay. Realistically, though, gas molecules do have volume, so we can't really have a volume of zero. Right? We couldn't have a volume of just zero. Okay, so low temperatures, all gases would condense and change state. So remember, as we lower the temperature of a water vapor, right? Water boils at 100 degrees Celsius. As the temperature gets colder, okay, or cooler, the molecules start to slow down. The kinetic motion decreases, and what's going to happen is pretty much eventually it's going to condense into the liquid form. Eventually, if the temperature continues to drop, it will eventually freeze, okay, into its solid state. Right? So technically, according to that, then that means there still should be a volume because it would condense into a liquid, but it's considered a hypothetical. Lord Kelvin used this reasoning as the basis for a new temperature scale called the Kelvin scale. And in the Kelvin scale, we actually have something called an absolute zero, which is the temperature in which technically all gases would cease to show motion and would have a volume of a hypothetical 0. So the starting point for the Kelvin scale, 0, as I said, 0 Kelvin, which is absolute 0. So when we're looking at 0 Kelvin, we are referring to minus 273 degrees Celsius. There are no degree signs or negative values in the Kelvin scale. Okay, so when we have negatives, let's say, one thing you are going to be asked to do is to convert your degrees Celsius into Kelvin for some of the practice problems that we'll have later on in this lesson. When mathematical manipulations are involved in studying gas behavior, you need to convert degrees Celsius temperatures into Kelvin. Okay, and it's going to look as follows. The temperature in Kelvin is equal to the degrees Celsius plus 273.5. So what we have is following. So whatever the temperature is in degrees Celsius, we would throw it in there. So if we were looking at something like 10 degrees Celsius plus 273.15, our temperature would be 283.15, but now the units are no longer degrees Celsius, but Kelvin. Now, we have this number, okay, the 273.15, but you will be, I will, for your calculations and the calculations that I'm going to expect from you guys, we are going to refer to it as 273. So here's a number you will need to memorize. So to convert any of your Kelvin and any of your degrees Celsius into Kelvin units, you're adding 273. Ignore the 0.15. So, Charles' law, the relationship between temperature and volume has since been known as Charles' law. So we've looked at Boyle's law, now we're looking at Charles' law. Boyle's law, pressure, volume. Charles' law, temperature and volume. Charles' law states that the volume of a fixed mass of gas is proportional to its temperature when the pressure is kept constant. Okay? So, we're not going to be referring to pressure, because pressure, when dealing with Charles' law, pressure will remain constant. So, if volume increases according to Kelvin, it is a directly proportional change, right? Temperature will also increase and vice versa. So if volume decreased, so would the temperature. So it's a direct proportion, as opposed to Boyle's law, where it was an inverse proportion, whereas one increased, the other one decreased. So the algebraic statement of Charles's law depends on using absolute or Kelvin temperature. So make sure that when you are making any calculations using Charles' law, you are converting your temperature into Kelvin. Okay. So this law is stated as V at T, where T is measured in Kelvin. So here we have the alpha. So V is proportional, right, to T. We saw this little symbol, this alpha symbol before. So V is proportional to T. And that was what I just explained a second ago, that if V decreased, so will T. So it's a direct proportion between the two. Now, so we have V is equal to some constant times temperature. That constant, we know, is pressure. Pressure is going to remain constant. So, in other words, what I did here was I tried to show that, but remove the proportional symbol and substitute it with an equal sign. Right? Remember that we've got some kind of constant. Okay, and when we rearrange this equation, we rearrange it as the following, where our constant is equal to volume over temperature. Okay. So what we have here is the following. This relationship only applies if pressure is kept constant and the temperature is given in Kelvin. If the temperature is given to you in degrees Celsius, convert it to Kelvin. And you'll see that when we go through some of the sample problems. Okay. If a sample of gas is collected at initial conditions I, we're going to use the letter I, this relationship can be rewritten as the following. Our constant is equal to our V, our initial volume, divided by our initial temperature. Now, suppose we subject a sample of gas to a change in temperature. Under the final conditions F, there will be a volume change, okay, showing the following. So, we know that same constant rule applies, right? Remember, the pressure remains constant. So we're subjecting a change to the volume or a change in the temperature, right? So we have our initial volume over temperature. We have the new change where it's been, where the temperature probably increased or the volume has changed, and we're trying to find what is the new temperature in which that volume is associated with. So, since both initial and final conditions are equal to the proportionality constant, Charles' law can be rewritten as the follows. The initial volume over the initial temperature in Kelvin is equal to the final volume over the final temperature. And really what this is if K1 here is equal to our initial volume over our initial temperature, remember, K1 is also equal to this, our VF over TF. Right? So we don't want to show all this. So we can ignore this K because we know that the pressure has to be constant. So we just kind of use a big equal sign to represent both of them. So if we have a volume here and the volume increases, right? So we go from a volume of, let's say, 2 liters to 4 liters, we've got an increase, which means whatever this temperature was, this temperature must have increased as well. Now, again, just to remind you guys, whenever we're dealing with temperature, make sure you do the degrees Celsius plus 273 to give us our Kelvin units. So, let's look at Charles' law here. So, notice now what's happening. The volume is decreasing as we're increasing temperature. So temperature's increasing, right? So we've got right up to 450, and notice how the volume's increasing, right? Because remember, it's just like, imagine heating a pop can, right? There's compressed gas in the pop can. You light a flame to it, right? And you heat it, and you continue to add heat to it. You're exciting the particles, the gas particles, right? There's carbon dioxide that's dissolved in the water of the pop. So you excite it. That pressure is building inside, and the volume wants to increase, and eventually, you can actually cause it to burst. Now notice what constant doesn't change, and that is over here, and that's pressure. So pressure doesn't change. So we don't worry about pressure, but as long as in the question, pressure does remain constant. And notice as the temperature increases, so does the volume, as long as pressure is constant. So Charles' law can be restated as the volume of a fixed mass of gas at a constant pressure is directly proportional to its Kelvin temperature. Right? Remember, we're converting to Kelvin, our temperature units. So notice here we've got pressure of the gas, and we've got a pressure of the atmosphere around it that is being exerted. Now, if we increase the temperature of our gas here, all of a sudden there's going to be an increase. There's going to be a volume change where the volume is going to increase here. But notice that the pressure, right? The pressure ultimately, right? We've got the pressure of the gas is increasing, right? Because all of a sudden, the kinetic motion is increasing as we're increasing the temperature. But eventually, it will pretty much stop, and the pressure that's being exerted by the atmosphere itself will equal the pressure that's exerted. So it's not going to pop the plunger off the container and such. So volume increases until the pressure exerted by the gas is the same as the pressure exerted by the atmosphere, and that's where both of these occur. So there really isn't a pressure change. Okay. There is a pressure change kind of until eventually the system pretty much reaches like an equilibrium. So, as a gas is heated from our initial temperature to our final temperature, the molecules move faster and collide with the container walls, more frequently increasing the pressure applied by the gas. This added pressure increases the volume of the container until the pressure exerted by the gas is equal to the pressure exerted by the atmosphere. Everything that I just pretty much explained using the diagrams, but just kind of in word form. So let's look at our first sample problem. Using a glass syringe, a scientist draws exactly 25.5 centimeters cubed of dry oxygen at 20.0 degrees Celsius from a metal cylinder. She needs to heat the oxygen for an experiment. So she places the syringe in an oven at 65.0 degrees Celsius. So she's putting it in a condition where the temperature will increase, and leaves it there for 30 minutes. Assuming the atmospheric pressure remains the same, what volume will the oxygen occupy? So now, your answer. So you should think of it in a logical form. So think of it as we're increasing the temperature. So what do you think should happen to the volume? Also, bless you. So start by listing your units, and remember, we are using temperature, but we're using temperature in Kelvin, so make sure your Kelvin temperatures have been changed. So take a moment, devise a plan to solve this problem. So what I have here are the following units. So these are given. So always start off with your given. Right? It's easier to follow along. And we have the following equation. But now remember, as I said, temperature must be converted. And remember, we're using degrees Celsius. So all we're going to do with both of these temperature units is add 273. So when we add the 273, we get 293 Kelvin and 338 Kelvin. So using what we've been given, what I like to do is substitute into the equation first. So start off with your blank equation with just the letters. So instead of VI, we're going to put in what our VI is. And we're going to have 25.5 centimeters cubed. Try to keep your units, because by keeping your units, it'll help you figure out what units get crossed out and what units you need to keep for your final answer. Your initial temperature is 293 Kelvin. Right. Our final volume is what we're trying to find. So we can just label it as, oops, what did I do? Our VF over TF, which is 338 Kelvin. So here now, pretty much, just going back to elementary cross multiplication and division and all those functions. We want to isolate for VF. So, because we have a number that's in the denominator, we are going to bring this across the equal sign and to the top. Right? So what we're going to have is 25.5 centimeters cubed, and it's going to be multiplied by the 338 Kelvin that we've just brought over. The denominator on that side remains the same, and we've just isolated for our final volume. So we're going to multiply the top two now. Notice here what units cancel out. Kelvin, cancel out. And our units will be in centimeters cubed, which are the actual volume units. So when we multiply our numerators together and divide it by our denominator, we eventually get 29.416 centimeters cubed. What are the least number of significant digits in my question?
3.
How many?
3.
3, right? This 30 minutes was in the question, but had nothing to do with the question. Right? It was just kind of telling us how long we were actually doing this little experiment. So we want the 3 significant digits, so 29.4. We look at the number immediately following the 4, which is a 1, doesn't affect anything. So our final answer is, our final volume is equal to 29.4 centimeters cubed. Okay. Next sample problem. A balloon is filled with 2.50 liters of dry helium at 23.5 degrees Celsius. The balloon is placed in a freezer overnight. The next morning, the balloon is removed, and the volume is found to be 2.15 liters. What was the temperature in degrees Celsius inside the freezer if the pressure remained constant? Notice, pressure has remained constant. Let's start off with our givens. Our initial temperature, 23.5 degrees Celsius. Our initial volume within the balloon was 2.50 liters. Our temperature change, right? What is the final temperature, which happens to be the temperature in the freezer that we're trying to find. And the final volume of the balloon lowered to 2.15 liters. So remember, the temperature, what we want to do is convert the temperature into Kelvin. So 23.5, we're going to add it to 273, and we're going to get the following: 296.5 Kelvin. So we have our initial equation, right? Blank equation, just put in the letters. So all we're going to do now is substitute into each one of them. So our initial volume, 2.50 liters. Initial temperature, 296.5 Kelvin. Our final volume of the balloon, 2.15 liters. And our final temperature is what we're trying to find. And a lot of times, students struggle when the unknown is in the denominator. To prevent that, my advice to you is you can flip both of them, right? Just like the sine law in math, right? If you just kind of flip. But if you're going to flip these two, make sure you flip these two as well, right? So what you can do is write it as follows: 296.5 Kelvin over 2.50 liters equals TF over 2.15 liters. You can do that if you want. Okay. Or what you can do instead of that, and I'll use a different color, is switch these two together. And what you're going to have, but it's going to add an extra step, and so we're going to have TF, right, over 296.5 Kelvin equals 2.15 liters over 2.50 liters. Right? So now all we're doing is bringing this over. So we're multiplying 296.5 by 2.15, which is exactly what we're going to do when we bring this over, if we use that method to isolate for our final temperature. So we're going to isolate for TF in any which way. And I'm going to use this bottom method here. So what we have is 296.5 Kelvin multiplied by 2.15 liters divided by 2.50 liters. Notice what units cancel out. My liters cancel out. And my temperature. Right, so when I multiply our numerators and divide it by our denominator, we are going to get an answer of 254.99 Kelvin. So we want, what are the least number of significant digits in my question? 3. So we want the 2, 5, and the 4, right? But we look at the number immediately following it, and we don't keep the 254, but it becomes 255 Kelvin. But if we want to relate it to our freezer, right, we're not going to refer to it as, well, the temperature of my freezer is 255 Kelvin. All right? We're not going to refer to it that way. So now, how am I going to convert these Kelvin units to make it in a temperature that we can maybe understand? We're going to what? Subtract it. Good. So we're going to take the 255 Kelvin, we're going to subtract it by 273 Kelvin, and we get a temperature of negative 18 degrees Celsius. So now, can we relate to that? Yes, we can. We know that that's cold. Right? You're not going to hear the meteorologist explain to you guys the temperature tomorrow and say, well, the temperature is going to be 255 Kelvin. That's what the wind chill is going to feel like. Is that cold? I don't know. Right? Then I got to do the calculation. Right? So I will accept this answer. Right? I may ask in degrees Celsius.
That question though, would ask in Celsius.
If it asks you in degrees, does it ask in degrees Celsius? Yeah. So it asks for it. So you have to make the calculation. But if it does it, you can keep it as Kelvin. Okay. So. Any questions about these? No? Good. Gay-Lussac's law. Most containers that are used to store gases have a fixed volume. If the temperature of a gas increases but the volume of its container cannot increase, what happens to the pressure of the gas inside, right? That pretty much goes to the example that I mentioned to you guys about, heating up a pop can, right? And getting the particles of gas really excited within this, compressed container. Okay? So the volume of the gas is equal to the volume of the container holding the gas. So if we have a gas in a container, the actual volume of the gas is whatever the volume happens to be of the container. Because remember, regardless of the container, right? If I've got a small container holding gas particles, okay? Let's say there are 4 particles kind of, moving around in that container. But then I increase the size of that container. I still have those 4 particles that are still moving around. So the volume technically is now whatever the volume is, right, of each container respectively. Right? So that's really what the volume of a gas is. The volume of a gas is always measured based on the container that it is in. Gay-Lussac's law states that the pressure of a fixed amount of gas at a constant volume is directly proportional to its Kelvin temperature. So notice now what we're referring to. We're referring to pressure. Okay. We're referring to pressure. We're looking at constant volume, right? Because the volume is whatever the volume is of the container, and being proportional to the temperature that is in Kelvin. So if temperature is given in kelvins and volume, and the amount of gas is constant. So introducing now a new proportionality. We're going to use, remember how we used K1 for the other one? We're going to use K2. So pressure is directly proportional to temperature, right? Charles' law, volume was proportional to temperature. So which means If I increase the pressure, what's gonna happen to the temperature? Also increase, because it's a direct proportionality. So here is the constant. So P is equal to our constant multiplied by our temperature, and we want to isolate for the constant to look as such. So our constant is equal to our pressure divided by our temperature, and this is Gay-Lussac's law. Right? Charles' law looked at volume, temperature. Gay-Lussac looked at pressure and temperature. So we're looking at very similar formulating of the actual equation for the gas laws. So if we assign an initial pressure and an initial temperature, and we'll have our final conditions as PF and TF, the above relationship can be rewritten as follows. So similar to Charles's law, right? V1I over Ti equals VF over TF, but according to Gay-Lussac, we're looking at pressure and temperature. So notice here, what is the volume of the container? So the volume, look at the two containers here are exactly the same. But what happens is, if I increase the temperature, notice what's increasing? The pressure. Because all of a sudden, look at the particles, they're moving, right? Gas particles are moving at its fastest. But if I continue to add temperature, right? It continue to increase the temperature, I'm going to force these particles to move even quicker. So I am going to increase the kinetic energy, or the kinetic motion of each of the particles of gas. So I'm exciting them, right? Think about the particles in a solid state and how they vibrate minimally. As I increase the temperature, I get those particles excited to the point where they start to melt. I increase those particles, I can continue to add heat to the particles of liquid, and the particles will evaporate. Right? They get more excited and they evaporate and they move in every which way. But I continue to add that heat and they get even more excited. So notice how this mathematical relationship is very similar to Charles's law. So here's Charles's law. Initial volume, initial temperature is equal to final volume, final temperature. Same thing, but now we're dealing with pressure and temperature, but what's constant? What's constant in this one? In Gay-Lussac's law, what's constant? Volume. Right? What's constant here? Pressure. So notice how, look at the letters that we've been using. Boyle's law, PV. Charles' law, VT. Gay-Lussac's law, PT. So notice how we're using all those pressure, volume, temperature. But it's really important that you know which one is which. And you see, we're going to see how they are all going to relate to one another. So let's look at the following sample problem. A cylinder of chlorine gas, Cl2, is stored in a concrete-lined room for safety. The cylinder is designed to withstand 50 atmospheres of pressure. The pressure gauge reads 35.0 atmospheres at 23.2 degrees Celsius. An accidental fire in the room next door causes the temperature in the storage room to increase to 87.5 degrees Celsius. What will the pressure gauge read at this temperature? So now we want to find out, is the gas that's in this container, will it be pretty much still within the boundaries of the 50 atmospheres? So point out what your givens are, and then work from there. So figure out what information in this question is actually needed and what isn't. What information really, what number are we really not going to use, but we might compare to it? The 50 atmospheres, right? So this is, we're not really going to use that, but we will maybe make reference to it with our final answer. So let's write out what our givens are. So our initial pressure, 35.0 atmospheres. Our initial temperature, 23.2 degrees Celsius. Temperature increases. So we're trying to figure out what is the final pressure. So the temperature increased from 23.2 degrees Celsius to 87.5 degrees Celsius because of the fire. So, first step, what are we gonna do? 273, right? We're actually going to convert these temperatures into 273. Now, of all the laws, we had Boyle's Law, Charles' Law, and Gay-Lussac's Law. Which one of them did not require this change in temperature? Boyle, because according to Boyle, pressure, volume was what we were trying to find. Temperature was what remained constant. So who cares what the temperature was? We don't need to make that conversion. But with these we do. So our initial temperature is 296.2 Kelvin, and our 87.5 degrees Celsius, 360.5 Kelvin. So we have our equation, our initial pressure divided by our initial temperature is equal to our final pressure over our final temperature. So all we're going to do is substitute. So our initial pressure, 35.0 atmospheres, over our initial temperature, which is 296.2 Kelvin, equals our final pressure divided by 360.5 Kelvin. And we're lucky here because our unknown is found in our numerator, so it's just a simple shift of the 360.5 from the denominator to the numerator, which treats this as multiplication. So we have 35.0 atmospheres multiplied by 360.5 Kelvin divided by 296.2 Kelvin, which is going to help us find our final pressure. Now notice Kelvin units are what cancel out, and our final pressure is equal to 42.5979 atmospheres. What are the least number of significant digits in my question? 3. So we want the 42.5. We look at the number immediately following, and our final pressure is 42.6 what? Atmospheres. Pretty good. So, should we worry about that temperature? It looked like it was a big temperature change, but it remained within the range below 50 atmospheres. So next class, I have the notes printed. We're actually going to combine all these laws together and form what we call the combined gas laws.